welcome everyone to this afternoon's symposium. It's the BMEX symposium. The X is for translation. And the talks today are really geared around the research, development, and translation of advanced and emerging ultrasound imaging technologies. We're really excited. We've got 4 invited talks and a keynote who we'll introduce in a moment. But I'm really happy that we're going to start with my colleague, Dr. Bell. Dr. Bell is faculty in electrical and computer engineering, also biomedical engineering at Johns Hopkins University. And she's going to get us underway with her talk on ultrasound image formation in the deep learning age.
Thank you so much, Jeff, for the nice introduction. And I'm glad we're all able to improvise so that we can start off with this nice talk about ultrasound image formation in the deep learning age. And so many of us who I believe are tuned in are familiar with ultrasound imaging and its benefits. And we are aware that it's applicable across a wide range of organ systems. And these benefits also extend for both diagnostics and interventional and surgical guidance. Despite these many benefits listed here, there are also several outstanding challenges that have persisted with ultrasound imaging in its 60-year history of existence for medical imaging. And these challenges are listed here, and at the heart of all of these challenges is the basic idea that ultrasound images are thought to have poor image quality. There have been several techniques to overcome this challenge, including spatial compounding, which smooths out the speckled texture appearance of ultrasound images, Doppler imaging, which allows us to see blood vessels and possibly segment blood vessels that are otherwise difficult to find, harmonic imaging, which reduces the acoustic clutter and allows regions that should appear black to actually appear black in the image, although there are cases where harmonic imaging fails, such as when we're imaging overweight or obese patients. And this is one reason why, as a graduate student, I introduced a coherence-based approach to imaging that reduces acoustic clutter, even in cases where harmonic imaging fails. Another advancement that we have is elasticity imaging, which allows us to image the mechanical properties of tissues. And then there are others that are not featured on this slide. Now, the commonality among all of these different types of techniques is that they all rely on the same raw data. They start from the same existence. And although they start from the same existence, none of these options simultaneously address all of the outstanding challenges that have known to persist for the past 60 years. And so this leads me to question, can we possibly have a single solution to multiple challenges in one step through the assistance of deep learning, which would allow us to transform noisy, poor contrast images into some desired image that only displays a structure of interest? So for example, if we start with our raw data that was used to create any of the images on the preceding slide, and rather than applying traditional beamforming methods to create this noisy image, can we instead use deep neural networks to create a desired image and then possibly cascade multiple networks together to find other features that are hidden in the same raw data, such as a needle tip? This idea was the topic of my Trailblazer Award from the NIH. At the time that I proposed this idea, I was not aware of anyone thinking in this direction. So I am very pleased to share with you some of our achievements to literally blaze a trail and show us what's possible in this area. Successful implementation of these ideas would be a significant improvement over the current state of the field and would overcome many of the challenges with poor image quality in a single image formation step. So to drive this big picture home a little bit more closely, motivated from a clinical example, let's take the case of a biopsy where you would normally want to remove a small piece of tissue to determine its disease state. Ultrasound would typically be used to identify where the needle tip is located. And as you can see featured here, some patients have very good quality and can tell you very clearly where the needle tip is located, such as patient A, and other patients, such as patient B, is not so much. It leads us to question things like, where's the needle tip? Also, where's the target? And if we want to apply one of the advanced techniques that I talked about earlier, it also begs the question of at what speed can we detect these structures in the raw data? And if we return to the first question of where's the needle tip, ideally we would want to, for all patients, determine where the needle tip is located and provide some sort of overlay despite the otherwise poor quality of the ultrasound image. And we can do this with assistance of photoacoustic imaging by inserting an optical fiber into the hollow core of the biopsy needle. So to provide an overview of photoacoustic imaging for those who are not familiar, you can think of photoacoustic imaging as ultrasound imaging with a laser, and together this creates your photoacoustic imaging system. And then if I have a target, such as my needle tip that I want to image, by inserting an optical fiber through the target, I can then place my ultrasound probe out as I normally would to see both the needle tip and the surrounding tissue. And then I would transmit light toward the needle tip, which would absorb that light, undergo thermal expansion, and generate a sound wave that I could detect with a conventional ultrasound transducer. And then after I detect my signals, the transducer contains piezoelectric elements that convert the mechanical pressure waves that are sensed into electrical signals that are then sent to the scanner, which receives the signals and sends them to an onboard computer for processing. The first step in the processing chain is the beamforming step, and typically beamforming is performed with a traditional delay and sum or DAS beamformer. This beamformer can be applied to both ultrasound and photoacoustic images, and it's the most fundamental beamformer that produced a lot of the poor quality images that ultrasound images are known to have. And so this is why we have advances based on mathematical models, such as the short-leg spatial coherence beamformer that I introduced as a graduate student. And these mathematical models are more complicated, they provide better image quality, but they're also more computationally intense. And this is the area where I believe we can make an impact with deep learning as well, where we could deliver the same quality and replace the computational expense with a network that offers both quality and speed. And then after we apply whatever beamformer of our choosing, we then might have some post-processing such as segmentation. And then finally, the desired image is displayed on the monitor. And the nice thing about photoacoustic imaging, being ultrasound imaging with the addition of a laser, is that we can interleave ultrasound and photoacoustic images to improve the overall experience and provide more structural information. So with that, I would like us to now look into those three questions that I introduced from the clinical motivation. The first being, can we use deep learning to detect needle tips, which we model as point sources? And we start with raw photoacoustic data as input to our network, and the network has three outputs. And if we look at example channel data, we see that there are a lot of wavefronts. And when we apply the conventional delay and sum beamformer to the photoacoustic channel data, we see that it's very difficult to detect where the needle tip is located from the photoacoustic data. And so if we instead pass the same raw data, not through a delay and sum beamformer, but through a deep neural network that was trained to identify point sources to determine where the needle tips are located, we can get what we see as these CNN-based images, where we could see very clearly where the point sources are located. And in this case, these point sources were obtained from not a needle tip, but a cardiac catheter tip, which shows the versatility of this idea, because as long as you model the wavefronts as point sources, our network can detect it. And this cardiac catheter was placed into an in vivo vein, and we're able to determine more clearly where the tip of the cardiac catheter is located with our deep learning approach, as opposed to the more traditional delay and sum beamforming approach. So with that objective achieved, and moving on to the second question of where would the biopsy target be, we've achieved this by testing multiple networks with different types of training data and different input-output schemes. And in the interest of time, I'll focus on this one network that we published on in IEEE Transactions on Ultrasonic Spiroelectrics and Frequency Control in 2020. And that network takes raw input channel data. And in this case, it's channel data from a patient treated at the breast clinic here at Johns Hopkins. And the output of the network is twofold. One is a DNM image that contains reduced clutter, it contains reduced speckle, and it shows us very clearly where the breast cyst is located in comparison to the delay and sum image. The second output is a simultaneously achieved segmentation showing us where the breast cyst is located. And if we compare this to the more sequential approach of first applying beamforming and then some post-processing to get a segmentation, we see that we get good agreement, but we also get this good agreement directly from the raw channel data. So the raw channel data is able to give us an image that tells us very clearly where the cyst is located, and a segmentation in parallel. And so this was a great achievement for our lab. And with this success, I'll move on to answering the third question of how can we deliver advanced beamformers without the same computational expense that would otherwise be required based on the mathematical steps required to get the better image quality. And I'll motivate this from the short lag spatial coherence beamformer that I developed, where if you're not familiar with it, it works by starting again with raw channel data, applying time delays, and then windowing the data in time and cross-correlating the windowed data in space in order to build up what we call spatial coherence functions that show the similarity of the correlated wavefront as a function of detected separations in the raw channel data. And then we would integrate this spatial coherence function to achieve 1 pixel in the SLSC image. And we then slide our window down to build up multiple pixels in the axial dimension. And this process is also repeated laterally. So we get the appreciation that this requires multiple cross-correlation calculations in order to build up an image pixel by pixel. And this is in stark contrast to the deep learning approach that I just talked to you about, where we would take the entire channel data, pass it through a network, and create a single image. So we can appreciate one operates at the image level and the other operates at the pixel level. And as a result of operating at the pixel level in order to improve image quality, it does introduce additional computational expense. And so if we look at the steps written out in this block diagram format, we can appreciate that the most computationally expensive step is the cross-correlation step. And so that's the step that we targeted in order to reduce the speed or improve the speed with which we can deliver this beamformer. That's the step that we targeted for replacement with a deep neural network. So we have the top pathway, which produces the original SLSC images. And in this case, you're seeing some example SLSC images from breast masses of patients from the Hopkins Hospital. And if we take the detour pathway to create these images by replacing the computational step that is otherwise requires multiple cross-correlation calculations and then learn the coherence functions through a deep neural network that we call CoherentNet, we get these images that are displayed side by side. So on the left, we have the original, and on the right, we have the case produced by the deep neural network. And we see very good agreement to the extent that we have a 0.93 image-to-image correlation over the entire test set. And we achieve this agreement while also achieving our goal of getting 3.4 times faster speed improvement in comparison to the DNN. And I'm excited to share that this, we just partnered with NVIDIA so that we can place this CoherentNet architecture on their GPUs to further improve the speed with which we can deliver these beamformers and create demos for the world to see. And in closing, I'll say, you know, a lot of this work is fueled by having large data sets and code that allows us to benchmark our data sets. And so we freely share examples for both ultrasound and photoacoustics, and highlighting the ultrasound examples for a moment, which is available at the website shown here and is an outcome of the challenge on ultrasound beamforming with deep learning, which was opened up to the entire community. So the website is cubdil.jxu.edu. And in this data set, this is the first data set that it contains internationally crowdsourced data from 7 ultrasound groups worldwide. And it contains a variety of simulated phantom and in vivo data obtained with multiple ultrasound transducers, multiple ultrasound systems, and it creates the dataset diversity that is really needed to drive this field of ultrasound image formation with deep learning. In addition to the crowdsourced data, that's the first of its kind, we also release open source code that anyone can use to test their network with specific benchmark criteria that's available in this evaluation code. And we also have a PyTorch delay and sum beamformer that can be used to implement a basic delay and sum beamformer in the same deep learning framework that you might be using to build other networks. And we also offer the feature of sharing the trained network weights from the winners of this challenge. So all of this is freely available to drive the field and accelerate research at the intersection of deep learning and ultrasound image formation. And I'd like to thank my team of co-organizers and my graduate student, Allison, who was very helpful with a lot of the post-caudal evaluation and dataset curation for making all of this possible, and as well as the winners and the multiple groups from around the world who contributed this data. And this challenge was sponsored by Verisonics, a leader in ultrasound research for these type of development, as well as IEEE and the Ultrasonics Ferroelectrics and Frequency Control Society. And again, this is the website if anyone desires to use it. And if we return to this roadmap of advances that I talked about earlier, my outlook is that deep learning is starting to be the next frontier. And with deep learning being the next frontier, a lot of the known challenges with deep learning applied to other fields still persist, such as the fact that we need training sets that include multiple possible variations. We need to be able to generalize across different systems and different target sizes and target shapes. And these two things are one of the features that is a resource provided through the caudal network to start to chip away at some of these known challenges and probably start to address other challenges, such as the ability to understand and interpret what networks are doing. Similarly, we must be cognizant that evaluation metrics must be tied to specific imaging tasks. And that's another reason why we released both evaluation code that's tightly integrated with the data that we released with the caudal challenge. And overall, returning to the big picture question that I posed earlier, I've also shown you that it is possible to get multiple outputs from a single input, either by creating a network that's designed to do so, or by cascading multiple networks side by side, but they can all operate on the same raw data. And I'd like to end by thanking my team of graduate students, collaborators, and funding sources who have helped to make all of this possible. And thank you all for your attention. Follow me on Twitter if you'd like real-time updates of what we're doing, and I'd be happy to take any questions.
What's that sound? It's in-person applause. So great.
It is great. This is actually my first in-person talk since COVID.
Excellent.
Started,
Thank you,
yeah.
guys. Thank you so much. I don't know how you covered that much in that amount of time, but you got us underway. And I'd like to take an in-person question. Anybody, please. Go on, you can do it. You're so shy.
Questions from students are certainly welcome.
Extra credit. If you're in my class, you'll earn extra credit for exercise number 4. Yes, please.
So we all know that neural networks are getting really good at solving a lot of these problems, but one of the biggest issues with them that comes up is their interpretability and their reliability, where sometimes it can make sensible looking results that are actually fundamentally wrong. Do you have any direction that you're starting to work on to address these concerns?
Yes, in fact, that's an area that I'm very intrigued by, and it came about because of this caudal challenge as well, in the sense that some of the submissions looked beautiful when operating on their own test data, and then when operating on the curated data that was never seen by the networks, they failed miserably. So I am interested in questions as to how can we not get tricked sooner rather than waiting until we have a curated test data set to understand that the network actually didn't work to begin with. And so that's certainly something of interest for me. I don't have the solution just yet, but maybe come find me in a year or so and I might have an update for you.
Thank you so much, Bizy. Here, let's switch over between laptops. Go ahead and stop your share.
Will do.
And I'll start it here. Thank you again, Bizy.
You're welcome. Thank you all.
All right, hopefully everyone is hearing me. And I just want to give an introduction to what I hope is our keynote speaker. Are we ready? Are we ready? Excellent, please. Excellent. All right. All right. All right, so while our keynote is getting set up, I want to give a quick introduction. But again, first start by thanking everybody for making time in their afternoon and joining us. Please feel free to enter questions in chat, and we'll take those at the end of the talk. And looking forward to this talk very much. I want to read from a really nice article about Dr. Scott. It says early fall 1976, GE had just launched its first CT machine. So that should calibrate you as to when we are in time. The first CT. Jack Welch, and hopefully you know Jack Welch. He was the head of what was about the biggest company in the world at the time. And he visited GE Research and asked, what am I supposed to do about medical ultrasound? And the next week, Scott Smith arrived at GE, a young physicist with his PhD from the University of Pennsylvania in magnetic resonance and condensed matter physics. And he joined a very quickly assembled ultrasound team at GE. Young Dr. Scott, it says, could not foresee the impact his work would have over 45 years. Two major imaging modalities, ultrasound and work in MRI as well, and several first of their kind ultrasound probes. It was clear that he helped to revolutionize medical imaging and enhance public health in the US and beyond. It's just a great example of how a scientist, engineer, physicist can have such tremendous clinical impact and benefit working within a fantastic industrial R&D environment. The technologies that have emerged over the last 40 years in ultrasound, many of them have Dr. Scott's fingerprints on them, but Dr. Scott is quick to dismiss individual credit. And he will quickly remind me that it was about the team that was with him. But I know that we have him to thank in no small part for the state of ultrasound imaging as we know it today. For 20 years, Dr. Scott has taught ultrasound imaging at the IEEE symposium, 500 or more engineers having sat his course. And I was so happy that we got a dose of that this morning here at Hopkins when he gave a guest lecture in the Radiology for Engineers class. Dr. Scott, without taking up any more time, I'd like to thank you very much for joining us today, and we're really looking forward to your keynote. Thank you, Dr. Scott.
Thank you very much. And I am really looking forward to the other people who are talking this afternoon. And happy to sing for my supper here tonight. Yeah, close enough. Good. I'm going to get rid of the videos here, unfortunately, so that you can see the full slides. But maybe you can see that on your own screen. Yeah. I really like the little icon that you have for this translational thing with a X, Y, Z coordinate system. And I'm going to say, I think we ought to be switching to a more polar coordinate system to indicate the place we really come from here on the left-hand side. And I tried to indicate where we are here with that little yellow dot. But we've got a lot of company here. The last time I looked, there were about 8 billion of us on this planet, about 40% of whom have access to some form of medical imaging. When I look and think about ultrasound, it's got a lot of things going for it. It's fast, it's safe, it's relatively high value, I'd say, diagnostically useful, and low cost, or if you feel that way, especially, well, low cost, especially compared to some things like MRI, CT, and things like that, or PET. And if you're a businessman, sometimes they even would like to use the word cheap. This leads us to the general feeling that ultrasound might be a nice thing to have pretty much everywhere for everyone. If you're going to somehow impact that other 60% of the world's population, ultrasound is probably a good way to go after that. Unfortunately, one of the problems with that is that ultrasound is a coherent imaging system, as has been pointed out, and coherent imaging systems in some sense are pretty hard to interpret. The picture that I have here on the far left is one that was taken with the very first ultrasound system that I worked on. So it's from just before 1980. let me tell you, we were absolutely thrilled to get that image and worked very hard to do that at that time. It looks a lot better when it's in motion, but it's still pretty bad. And when you compare it to the sorts of things that we're doing now, it's really kind of amazing how far we've gone. And the point that I want to make is that if you go from that 2D sort of thing where you've got lots of individual particles and a volume element scattering and you get coherent noise from it, it's a lot harder to see what you're dealing with than after you've smoothed it out a little bit with some more software. So, you know, sort of the thought is, can we get to the point where we can do 4D sort of everywhere? And I'm going to use that as a theme of going forward, where 4D is the idea that you've got 3 spatial dimensions and time being the 4th one. Advertising hype, I think, but nonetheless, I think a useful way to look at things. So let's look at the fundamental problems here. I mean, the problem here is that, frankly, you have to send ultrasound into the body and wait for it to come back, and it travels at a nice finite rate that I've indicated here. The problem with that is that it's what, something like 10 to the 5th times faster or slower than light waves. So it takes a while to make these images. And what do you want? Well, you'd like to have image quality. I think what we're really talking about here is resolution. And then you'd like to have field of view, the biggest thing you can see, and how fast can you update that? Those are all neat to have. Now, can you get all of them at the same time? Well, no. You tend to have to trade-offs. Engineering is trade-offs. So the example that I've got here, you can work through the numbers, but you know, 1 volume a second or so is not uncommon for what you can do. So how would you go about doing something sort of like that? Well, here's the simplest version, and that's to take a ordinary 1-dimensional phased array imaging. This one's a convex array. It's mounted on a obloid structure so that you can rotate it about that 1 cylinder or axis, and then see how that wobbles back and forth. You know, what's its advantage? Oops. The advantage of this is that it does allow you to build up that 3D spatial image. The 2D image quality from any individual plane is relatively uncompromised. And the nice thing about it is that it doesn't require any big changes to the hardware, right? You can just plug one of these things in and then do in software all you need to generate the rest of the image. However, it is limited, as it says here, with certain difficulties with actually making this thing wobble back and forth in a stable way. And in particular, you need an awful lot of good motion control to align images. The other thing that's not necessarily entirely obvious here is that you typically have a shell over this thing. You don't want the wobbling thing on your surface. And that tends to be a place where you end up having all sorts of inner artifacts come about. So how do you get around some of these things? One way is by being a little more clever in your beamforming. Here the idea is that the transmit beam is a little broader than the receive beam. So you can fire 1 transmit beam and then get multiple receive beams coming back from that. How well can you do that? It varies, but you know, 2 is nice. 2 for the price of 1 is not a bad thing. You can get 16, maybe even a little bit more. So a substantial way to increase the volume imaging rate and sort of the fundamental basis behind all of the electronic 4D imaging. When we talk about that 4D imaging, one of the advantages of doing that with a purely electronic array is you just develop incredibly more sophisticated ability to control the agility of the beam. And so instead of being stuck with what the motor's giving you, all you have to do is change the beamforming coefficients in the code. You can pretty much steer the beam any place you want at any time. That turns out to be especially useful in some very specific clinical applications, but no matter. It turns out that there is a little bit of simplicity because the left side of the beamformer is really pretty much like the right side. And so if you use that symmetry, you can simplify some of the hardware construction dramatically. That's again 2 for the price of 1. And you know, the downside here really But something that's job security to a transducer engineer's heart is the fact that you end up getting huge numbers of transducer elements, and that then, frankly, the transducer isn't the problem, but managing to connect that to a beamformer is where we make our exorbitant salaries, whatever, yes. And then dealing with all the problems associated with putting a beamformer into the probe. Now, there are a couple different approaches to dealing with that kind of strategy. The first one has to do with so-called sparse arrays, where you make a fully dense 2D array, but take out a lot of the elements. So maybe only 10 to 25% of them are left. That ends up being useful in the sense that it's a lot easier to build the probe. It tends to be a lot less useful in the fact that the image quality that you tend to get is pretty poor. You're fighting artifacts all the time, braiding lobes, low sensitivity for the system, so weak penetration. The alternative is to make arrays that are fully dense, typically with element counts that start off on the area of 2,000 to 3,000 elements in the system. That's a lot more than the number of channels in the system. So you end up having to put some kind of beamforming electronics into the probe. A lot of times that means a relatively high voltage for transmit, much lower voltage to receive. So the ASICs that you end up dealing with there are sort of unusual in that most common signal processing ASICs are all low voltage things, and then high voltage things are usually separate in a different semiconductor process. You end up with the standard sorts of packaging problems that are listed here. If I talk about how you then manage an individual 2D transducer array, I can think of doing that in essentially two different ways. The first way is what I'm going to call this 2D matrix array, where you use a bunch of switches in the array to connect different groups of elements together. And by reconfiguring the way those switches are, you're able to change how the beamforming is done. So it's essentially converting that two-dimensional array into a one-dimensional array for the purposes of beamforming. So I think there are a bunch of pictures here that show this. Yeah, here are all the elements connected in individual columns so that you're able to steer using your beamforming channels left and right. I think we have the next one. Oh, maybe not. Okay, I think there were supposed to be rows in there. But here are ones where they're on diagonals so that you're now able to sweep top left to bottom right, if you will. Of course, you can do it in the other direction as well. And now with a little luck, yeah, okay. And here's a quarter of an annulus, right? So that you're using things that make concentric circles, like, I don't know, annular arrays. Good for large apertures. I think that's all it was, right? Okay. Now, the other approach is to use what's called a sub-aperture beamformer. The people who talked about this in the literature first actually were from Philips. And the idea was that you take a subset of the full aperture and connect those elements densely to a sub-aperture beamformer, I'm going to call it here. So there are typically analog, very low power analog ways of doing that beamforming and doing phase rotations or delay lines, passive delay lines, whatever sorts of things. And those are, if you will, the small delays or the fine timing changes. And then the big timing changes you leave to be done back at the system end, usually in the console, but not necessarily. This gives you the opportunity to do those fine little bits of steering and focusing within that sub-aperture part, and then do the dynamic focusing and the full aperture delays back in the system beamformer. So that cuts as many thousands of things down to many thousands divided by 9, 25, 36, whatever. But a sort of reasonable number of channels. And so here's one implementation of that for cardiology. Okay. So this was GE's first big E4D cardiology probe. For scale over here on the left-hand side, I show the transducer array. If you want to understand what the appropriate scale here is, that curved thing is a strand of my hair. I measured it, it's 80 microns in diameter. And you can contrast that, there's that little thing sitting up on the top. That's one element of the transducer array that we picked off from the side that's not in the image there. And so you can see that it's maybe of order 200 microns on the side, maybe, and 400 or 500 microns thick. A bunch of stuff there. That's at the very front end. Then there's a bunch of electronics in here. Don't take the number of circuit boards very seriously, but there's more than one. And there are a couple of application-specific ICs in there on each board. And there's some magic that's used to connect all of those things to the transducer array. When you're finished with that, you get these pictures where simultaneously you can get a couple of different planes and then fill things in. And my argument is that when I look at a picture like the one on the right, I don't need to be nearly as clever a radiologist, sonographer, or whatever than I had to be to look at those 2D images that we showed at the beginning. Of course, after you've figured out how to do all this stuff, the next thing they say is, well, yeah, that was really nice, but can you make it smaller? So here's an example of that for a pediatric cardiology array. So the frequency here is, I don't know, maybe a factor of 3 higher. And so all those dimensions get a lot smaller. But yeah, you can sort of go ahead and do that as well. And then, of course, they say, can you make one that you can swallow? So here, the transducer array is about the size of your fingertip, maybe a centimeter on a side. And it still has those several thousand transducer elements, and you still have to get connections to everybody, and you still have to get all that information out. The way we got around that is indicated here on the cartoon, where you can see the transducer array in one place on the top, if you will. And then there's sort of a greenish thing underneath there. That's supposed to be the application-specific IC. It's in there. And then those orange things on the side are supposed to be a flex circuit that's made out of Kapton. And somehow that all can be put together and sort of works. It turns out that I was surprised that it turned out that these devices had become essentially essential for the ability of doing a particular operation called TAVI, which is an aortic valve replacement. And, get used an awful lot. The latest and greatest version here, they've upgraded the software mostly, although yes, we do have a new version of this probe. Yeah, this was I've also mentioned this was a big enough deal that we got a big company award for it. So that was a nice thing. And in case you haven't noticed, there's sort of been a theme here. Can you make it smaller? Well, the next idea that you can at least talk about is the idea of going off and doing catheters. And the catheter part, I think, is the place where you now imagine being able to put something in an individual meter in diameter, or something where you want to put it into the heart and look at what's going on, typically while you're doing some other form of therapy there. And those tend to be about 3 millimeters in diameter. In one case, you tend to look radially or in disc or cone images. In the other case, you tend to make sector images off to the side. So here are the radial versions, the IVUS catheters. Both of these are from other places. Boston Scientific and Volcano have done the kinds shown at the top, where there's typically a piece of piezoelectric ceramic here that then spins on a rotating drive cable. And then the other version is a phased array that then has a switch ASICs embedded in the catheter tip. Both of those are out there now. And then the alternate, oh, we jumped through that. The other one is phased erasing catheters. Siemens has one that came out 15 years ago now, I guess. That's a single phased array, 64 element side viewing. And their later version of that takes that array that's 64 elements long and twists it a little bit. And that way they get effectively, by using different parts of it, a 3D view. So that's one approach to that. The GE version of that in the lab is this hybrid where we took a small phased array and mounted it on a motor where this is 3 millimeters. So there's 2.5 millimeters, and there's a 3-stage planetary gearbox running the motor with that, so that this wobbles back and forth, and then correcting for all the lags caused by the inertia inside. As you might imagine, those were hard to make. And here we've taken a real honest to goodness 2D array, managed to squeeze it into the tip of a catheter like this. And again, put the ASIC right behind the transducer array, encapsulate the whole thing, and do it at a cost where you can throw them away, which I find kind of amazing. This has just been introduced as a product by the Biosense Webster part of Johnson & Johnson. And I don't want to suggest that we're the only people who do interesting things here, that in fact, there are a bunch of things, and especially handheld products that are now available. Butterfly Networks has come out with what I think is a really interesting one that's based not on piezoelectrics, but on CMUTs. And then a couple of new products, well, a new product from GE earlier this year that's a wireless probe with, frankly, somewhat better image quality than you got from the other one, I believe. But a very nice combination of being able to do big aperture stuff as well. So with that, with the basis of here's how you make E4D arrays, now what can you do with them and what are some interesting things that are possible? And so I wanted to talk a little bit about this project that has been done in collaboration with folks at the University of Washington. Brian Bernards is the PI there, and we've worked with lots of people in his group and adjoining folks there to build a magnetic resonance compatible E4D probe for motion management during radiation therapy, something that I think some of you have some interest in as well. And the fundamental problem here is that when you're trying to do radiation therapy, the patient is frequently moving around a little bit with respiratory motion. In the liver, people have measured up to 30 millimeters of motion. And if you've got that much motion, you have to make clinical targeting volumes a little bit bigger than the area where the tumor is, and then the planning target volume for positional variation even bigger than that. So to the extent that you can decrease that, you can decrease the amount of collateral damage that's being done. And this happens, or this kind of process is being done in a couple 100,000 patients a year just in the US. So we'd like to see if we can do better. You know, how do you deal with emotion today? There's sort of 3 big ideas. Can you get people to hold still? And especially in the liver case, by the time you come up with different ways of doing that, the people who really need this have a harder time being compliant than a lot of people. There are marker-based methods that have advantages, but also some disadvantages, in that you have to implant them with surgery. And in particular, some of them don't stay put as well as you'd like them to. And finally, although there's some other sort of markerless approaches, but they tend to, well, in fluoroscopy, you end up using more dose, and some of the other ones, integrated MR and radiation therapy is unusually expensive, I would say, and robotic arms just haven't caught on very well, seem to be awkward. So our, at least, approach was to try and find a way to be able to take one of these E4D arrays and just strap it to the patient so that it's got enough field of view to deal with whatever you need to, and just leave it there. And we can use the E4D aspect to steer around and see what you need to see. The details of how we actually deal with the motion are suggested here, in that you do an acquisition ahead of time with both MR and ultrasound, and then during the radiation therapy, you're able to use the ultrasound to do the motion observation, correlate that with the MR things if you need it for detailed tissue segmentation, if you will, and then use that to trigger the beam at the appropriate times. So what's the probe look like? Again, this is one of these things where you can sort of build it up. We'll go through this pretty quickly. The probe is a big flat area here. It's relatively lightweight as these things go. There's a contraption here on the side that you won't see in general that holds a belt that you can use to strap it on the patient. Because it is so big, the aperture is so big, it's made up of these 3 individual modules here that we'll talk about in a minute. The ASICs in it dissipate enough heat that we went to the difficulty of putting in an aluminum heat spreader and EMI shield. There are these 3 modules, each of which has 6,000 transducer elements in it. So this is about an 18,000 element transducer array. It's big in a bunch of different senses. And it has the ASICs right behind them, the way the other one did. There are a bunch of sort of interconnect things, issues, and then how you control stuff that we don't need to worry about here so much. What you do need to worry about is if you're going to use this thing in the middle of an MR machine is you better not mess up the MR image too badly either. And so there are lots of different parts in these things that tend to interfere with ordinary MR imaging, and one has to go through and find them all and correct for them and make them not so ugly. So one of the big ones turned out to be one of the interface acoustic matching devices that we had in the transducer array that had a relatively large amount of ferromagnetic content, although you wouldn't necessarily expect that based on what its name is. And we found a way to make that material without so much ferromagnetic content and change it a little bit. So you can see the difference between burning a big hole in your image and having pretty close to no impact. And then the other big one had to do with the flex circuits that we built, which the ordinary way of making flex circuits includes a fair amount of nickel in the way the traces are built up, as well as in some of the components in them. And so you go work with manufacturers to get rid of those things as well. So that's what it looks like when it's all finished. We'll give you a beauty shot here. And then this is what it looks like when you actually get it into the lab. The other thing you have to make sure of is that everything's still going to work, even though that it's in the fringing field of a bunch of radiation. So we've put it through 35 gray cumulative dose, and so far everything is good. We have not tested it to failure yet. The acoustic performance, I realize this is a specialist slide, but for this audience, the pulse is pretty narrow. 3 half cycles is the best you can do, and maybe a little bit more than that. An average off-the-shelf transducer array you buy from the manufacturer comes with a -60 dB bandwidth of something like 70 or 75% fractional bandwidth. This is up at 85%, so that's on the good side. Can you make all this stuff work together? Here's an example, just testing it out on some phantoms, but you can see this is in fact a single frame picture. So on one side, you can look into the magnet room and see the probe with its unusually long cable. We had to do some fun engineering with that. That then goes through a panel in this wall over to the ultrasound imaging machine, which is in the background there. And now, with a little bit of luck, if this video plays appropriately, you may be able to see on the very bottom that 4 seconds into it, it will go from being very clean on the bottom to having a bunch of streaks that go vertically. The streaks going vertically is when you turn on the MRI machine and you get those high voltage. In this case, this is a 3 Tesla MRI machine, so it's 130 megahertz or thereabouts. RF, and some of that leaks through, but for the most part, it looks pretty good. And hope, yeah, and then here's what it looks like with real people. So this is great. This was just published, I believe, July 1st, I think it was, in Physica Medica. And I'm sorry, I think that one's supposed to be running too. So at any rate, yeah, you can. Here's where the probe is on the MR image, and then there we go. It's the ultrasound in 4D at the same time. So we're real excited about this because we think not only will it work very nicely for the particular application here that we had in liver, but also in lots of other kinds of combination modalities, if you will. And with that, I'll just finish off with a couple of slides. We're really excited about a new grant that I don't, should issue any day now, so to speak. We got the SCLER report back in March, I think it was. It came in at 2% or something like that. So Matt O'Donnell's a PI on it. It's a photoacoustic grant, and it's aiming to do real-time multispectral photoacoustics and ultrasound in a, if you will, more clinical setting. So one box that you can roll in and just put the probe on the same way you would an ordinary ultrasound imaging machine. So what's the big advance here? Really, it has to do with the kinds of lasers that are available. I want you to note here the important scale factor, which is a Sharpie, okay? And so this laser is approximately 35 to 40 cubic Sharpies. Okay. Whoa. Hold on. Okay. And if you want to get a single wavelength, it's of order. I can do that. This is 1 cubic Sharpie, and this one's about 4 cubic Sharpies. Okay. So you've taken something and you've reduced it in volume by a factor of 10, roughly. It's multi-wavelength. It goes about 200 nanometers. Its pulse repetition frequency is a kilohertz as compared to 10 hertz over here. Okay. The sequence in which it can go through individual frequencies is completely programmable. It's entirely flexible. And the only problem that I saw is that, and well, here's the example of what you can do with it. You see the thing that's coming in on the left is a needle, and then the injection, in this case, of gold nanoparticles. These have typically been used ex vivo. The classic example from Washington lab here is the transducer probe. You can see fiber optics coming in here on the side and some sort of complicated plastic housing. And our vision is, or what I want to do is I want to turn this into one probe that looks like every probe that you've ever seen before. And we'll put the fiber optic cables coming out the back end someplace so that you don't notice it. Pay too much attention to it. And that way we ought to be able to get these things to work as much more clinically relevant devices. So I guess I said all of this before, but here we are. Yeah, so I think that's about where I wanted to be at this point. I want to thank, I have not gotten everybody here, but the people on the left are people that I've worked with at GE's research lab, the probes team there. The people on the right are from one of many GE healthcare ultrasound probes organization. Most of these guys are from the group pictures, the team in Nice, France. There are a couple guys on the top who are also from the facility that builds probes in Phoenix, Arizona. And special thanks to the people who run the probes engineering organization, or probes general managers actually, from GE Healthcare, who've continued to fund us for a lot of this stuff when we aren't using the taxpayer dollars. So with that, I am probably over time, but
thank you very much, Dr. Smith. Rounding applause. It's been so long. So stay with me here, if you would, and then we will simultaneously swap over to our next invited talk. And give us just a moment. Dr. Smith, if you would join me over here in the question and answer area.
Oh, yes, indeed.
Well, Dr. Ding gets his laptop set and displaying. Let's see here.
Oh, okay. It would be helpful if I read the chat.
Excellent. Okay, so I'll read this out loud. There's the first question comes from Dr. Nick Durr. He's faculty here at Hopkins BME, and he says, this question relates to an idea you brought up in the beginning of your presentation about bringing medical imaging to the 60% of the world that lacks it. In thinking about expanding ultrasound use in low resource settings, what are the current major barriers? I wonder how you'd rank the barriers in hardware, software, training, business models, or others that are the bottlenecks to more widespread use in these areas.
Wow, that's a great question. And if you have good answers to it, I think you could become a business manager. I won't, so I hardly think I'm capable of answering it, but that won't prevent me from talking anyway. I think things have to become cheaper in general, okay? But they are, and they have been a lot. If I look at what even just the average cost of an ultrasound machine has been over, my career, and especially the last even 20 or 30 years of it, it's been dropping, not a lot, but maybe 3 to 5% a year, something like that. And we're going to see that continuing. One of the things I didn't mention, I probably should have, is that last week at the International Ultrasonic Symposium, a company like Vermont, which is a relatively small but an OEM probes manufacturer, started offering an ultrasound probe that has a USB connector on it. So you don't need an ultrasound machine anymore. You just take the probe and plug it into your whatever and get some software, which I think they will provide at least a starting version, but it's open source. And so people are going to be able to do some things like that. So I think that's going to be part of it. I think the fact that you have an infrastructure where the internet is going to become, to the extent in the certainly the first world countries, it's already completely available pretty much. And in even second and third world countries, you're seeing things where you don't have telephone systems of the kind that we used to have here. We just go strictly to the internet and wireless sorts of things. So I think part of it's going to be infrastructure driven, and I think the other part's going to be, frankly, some element of Moore's law driven, if you will. Good.
Excellent. Thank you very much, Dr. Smith, again. And I know we have more questions, but we'll, in the interest of time, we're gonna get to the invited talks, and then hopefully we'll have time for a great panel discussion and more questions at the end of this. So more resounding applause for Dr. Smith. Thank you very much. We really appreciate it. We're really honored to have you here as our keynote. Thank you. All right, and so now we will continue with invited talks, 3 more, and the first is by Dr. Kai Ding. Dr. Ding is faculty here at Hopkins Radiation Oncology, and his talk is on ultrasound-guided radiotherapy for pancreas cancer. Thank you, Kai.
Can you see me? Okay, perfect.
Good, and are you unmuted? Yeah. Excellent.
Now, you had the main dish. I'm going to give you the appetizer. So,
Dr. Smith mentioned about the radiation therapy and ultrasound combination, and they are married to have the ultrasound and MRI together. So now I'm going to talk about translation in. Translational research about using the ultrasound guidance in radiotherapy for pancreatic cancer. So here's my disclosure. Some little bit background about pancreatic cancer. So it's a third leading cause of cancer-related deaths in the US, and it's projected to be the second one in the year 2030. And our patients usually come with late presentation of the disease. So only about 15 to 20% of patients are considered resectable. And even after the resection or the Whipple surgery, the patients has very low survival for after 5 years. So for example, it's 25 to 30% for nodal negative disease and 10% for nodal node positive disease. However, there's a hope. More recent data suggests that outcomes may be improving over the time. So for example, the JCL paper from Hopkins showed that based on the autopsy data, 30% of the patients actually die from the locally destructive disease. And then from MD Anderson data from 2016, they showed that with a higher biological equivalent dose, larger than 70 gray, it can actually improve the overall survival. So at Hopkins, we treat the pancreas patients before they go to surgery with stereotactic body radiosurgery. And then we use 6.6 gray times 5 fractions. And we also use a breath hold to mitigate the motion. So here, example picture of the setup with our patient under radiation therapy treatment. So as you can see, the patient will have a breathing tube to help them to control their breath. And also we can see a linear accelerator with a gantry rotating around the patient body to deliver the focused radiation to the tumor target in the abdominal area. And then we also have onboard imaging systems such like cone beam. You can see that X-ray tube on the side and the panel on this side. So those are used for CT, cone beam CT to set up the patient. So what we do is we align the patient by comparing the onboard cone beam CT versus the planning CT. And then if there's a difference on the location, we use a robotic couch, you can see here, to move the patient to the target, the isocenter of the radiation beam. So one of the most important step in the radiation therapy is the treatment planning. So the treatment planning is more like an optimization process. We try to give the prescribed dose to the tumor target area, and then we try to minimize the dose to the surrounding normal tissue. One of the major challenges in pancreatic cancer treatment is anatomy. As you can see here, the tumor target is in the middle of the abdomen. And then we have all those normal tissues like stomach, duodenum, small bowel, and also kidney, liver, cord around the tumor target. So when you want to deliver a prescribed dose to the tumor target, you have to deal with the normal tissue around it. So how do we solve this problem? So we developed a procedure. We use endoscopic ultrasound that can be used to go to the duodenum, which is next to the head of pancreas, and then we will inject the hydrogel between the head of pancreas and the duodenum to separate the two. So on the bottom, in the bottom, you can see the left is endoscope ultrasound image before we inject the hydrogel, and then on the right side, you can see the hydrogel between the dark area, which is the head of pancreas, and this part is the inside the lumen, is the duodenum. So you can see the separation. So I'm going to show you a movie. So this is a hydrogel we injected. So this hydrogel is biodegradable. It will go away after 6 months. So nice thing is after 6 months, the patient will no longer have this hydrogel. So we only have that during the course of radiation therapy treatment. So that's a benefit of having this, and it can help us to separate the target and the normal tissue so that we can give a prescribed dose to the target. And then looking at the planning perspective, we can see with there are 3 pictures. The first one is a pre-injection plan with the PTV, which is a target as a priority. So in this case, without hydrogel, if we want to give prescribed dose to the tumor target, which is a red region here, we can achieve 95% of coverage, which is prescription. But however, our duodenum dose will be, the volume receiving 20 gray will be more than what we are allowed. So it violates the constraint. On the other hand, if we want to protect the duodenum giving the prescription dose, it can only achieve 80% of the prescribed dose volume we want. So in that scenario, we will not be able to achieve both the prescribed dose and also the limited dose to the OER. So the rightmost figure is the one when we after inject the hydrogel, which is also with iodine. So you can see it from CT. So those bright spots are the ones with the iodine hydrogel, iodinated hydrogel. So you can see them nicely separating the duodenum and the head of pancreas. And then with this approach, we are able to achieve both dose constraint to the normal tissue, the duodenum here, and also the target coverage. Another major challenge in pancreatic cancer radiotherapy is the motion. As Dr. Smith already mentioned in his talk earlier, we are trying to solve this problem by multiple ways. So one way is you can control the patient breathing patterns. For example, you can ask patient to do breath hold. Another way is you can give a large area to irradiate, so it covers the tumor area. But the problem, of course, is when you have such a huge area to irradiate, you will irradiate the normal tissue around. So here's an example of theoretical treatment window. So this red area is, for example, the region we want to treat. We only want to treat the tumor when for example, the vessel, here's a superior masonry artery here. Once within the window, we want to start the beam and to deliver the radiation. But the problem is you probably cannot see them well under the CT. Those vessel and soft tissue are only visible under MRI and ultrasound. So that's why we turn to ultrasound and start to develop methods to use ultrasound to guide the radiotherapy for pancreatic cancer. So this is our initial prototype of ultrasound probe that has been mounted on a bridge that is also mounted on the treatment couch. And with the acquisition of the ultrasound with the CT together, you can see we can nicely overlay the ultrasound on top of the CT. So the advantage of doing this approach is that our physicians are usually not familiar with the ultrasound display. So this way, when we contour the organs for the normal tissue and target on the CT, we can simultaneously bring the structures contours to the ultrasound. So through the process, our physicians can also learn their textures from the ultrasound, and in the future can help us to better utilize the ultrasound. So we also look at the probe impact on planning. So when we have a probe on top of the patient body, you may worry that if we may lose the beam path. Basically, if you you don't want to have the beam going through the ultrasound probe. So if you use the other beam angles, will that impact our treatment quality? So the answer is it won't. We are able to achieve same treatment quality, planning quality by avoiding the probe location. So we can treat the beam, use the beam from the side and also from the posterior side of the patient, and then achieve the same treatment planning quality. And the nice part about using ultrasound is we can now use the ultrasound to monitor the motion. So here's one patient under a breast hold, and we can see we can monitor the target by looking at each breast hold, whether it's the location is consistent throughout the different breast holds. One problem with those manually held ultrasound probe is reproducibility. As we all know, ultrasound is very dependent on the user. So the problem is, for example, when you have a probe on the patient belly, you can push a lot to get a crystal clear image, or you can push a very light and then you get a lousy image. So how do you solve that problem? So our idea is to use a robotic arm and tracked by an infrared marker. And this by doing this, we are able to reproduce the position and pressure using a robotic arm. And also because of the daily anatomical change on the patient, a lot of times, for example, if you place the probe back to the exact same location, a lot of times the target may be not in the same location, because you can imagine patient have a daily anatomy change. So the nice part about ultrasound probe controlled by a robotic arm is that it can automatically find the target for you by moving the probe around. Still, this like Dr. Smith mentioned, with a robotic arm, it's a kind of complex, and for daily use, there will be a lot of headache. So the next step we have been working on recently is to develop a flexible ultrasound transducer that can be similar to the E4D probe that can be worn on the patient body, so that it's easier to use. So this project was previously a collaboration with Hitachi, and for our proton system. So for our treatment, we want to have this probe, a transducer on top of the belly, and then it can go to two different directions. And then there's several challenges in the beamforming. So because we don't know the geometry of this transducer, so when it will introduce incorrect time of flight, and then you have wrongly delayed data, and the final result, you will have a distorted beam mode image. Our initial approach to solve this problem is to use the infrared camera, and then we just attach a bunch of reflectors, infrared reflectors on top of this transducer. So our initial result is that we can monitor the radius of the transducer, but the problem is, so I'll show you the initial result. So we can see the left side is the distorted image without any information about the transducer element location, and on the right side, after incorporating the transducer shape from the infrared camera, you are able to correct the image. You can see the contrast is much better. The problem is, in real clinical use, your infrared marker can be easily blocked by, for example, other imaging devices in the room. And also, as we know from ultrasound, if you are off by half of the wavelength, it may introduce other artifact to your image quality. So the ideal scenario is that we hope we can use we can use the image acquisition without any reflectors. So we developed a deep neural network, and then we take the raw image channel data from the transducer, but then we will not use any shape information from the transducer. And then by simulating a large amount of raw data from the transducer with different curvature and target, we train our neural network, and then we were able to generate the images directly from the raw data. So here's the result of our recent published TMR paper. together with YZ. So we have the leftmost is the target results. The second row is wrongly delayed data, and then the rest are the different networks. So as you can see, with our neural network, we are able to achieve similar image quality as the target reference image. So with all that, I hope you all enjoyed the talk, and for the take-home message, I'd like you to know that for our ultrasound applications, we can use endoscope ultrasound to guide the injection for the hydrogel, and then we can also use use ultrasound for motion monitoring. And I'd like to thank all my colleagues and collaborators. And any questions?
Great, thank you very much, Kai. And we'll take question and answer here at my laptop, and I'll like to invite the next invited speaker up. So there's a question, Dr. Jing, in chat. Go ahead and stop your screen share. And the question is, how did I think CNN generalize different shapes of the flexible transducer, or the DNF, but how did the CNN generalize to different shapes of a flexible transducer?
So that's a very good question. So okay, that's a very good question. So during our training, we were only able to simulate the flexible probe with a different radius. So that's one of the drawbacks. For example, if you have a S shape of the transducer, our trained model will not be able to produce a nice image. So what we are thinking is we want to have a combination of the the infrared reflectors to have an initial estimate of the probe or transducer shape, and then combined with fine-tune deep neural network that can do some certain adjustment, but not a lot. So that way, maybe we can have the benefits from both ways.
Great, thank you very much. Excellent, thank you for the question as well. Excellent. And so with that, I want to move on to our next invited speaker. And looks like you're ready to go. Can you share your screen, please? Not there yet. Now it's coming. And your video. And unmute. Testing 1, 2, 3. Testing 1, 2, 3. All right, I think.
Test 1, 2, 3.
And go ahead, try again. And you want to put that back in. And, all right. And I think you're ready to go. Excellent. Okay. Thank you, Amir. Sorry about that.
Thanks.
Now, so our next speaker is Dr. Amir Manbachi, and Dr. Manbachi is faculty with us here at Hopkins Neurosurgery, and he's going to tell us about the emerging technologies for ultrasound imaging in neurosurgery. Thank you, Amir.
Thank you. Thanks, Jeff. You don't see the screen?
Okay, hold on just a second. Something is happening. Stop share. Start share. We're going to share the whole screen. Looks okay to me. Better? All right, excellent.
Thank you. Thanks, Bison. Perfect. Thank you for that, Boise and Jeff. And thanks for the amazing talks, Kai, Scott, and I look forward to Emad's talk. Boy, it's really difficult to talk about designing and building a transducer after Scott, after hearing GE. So I'm an academic. If anything, we just started our lab last week. So the type of stuff you're going to see, I'm going to call it a prototype. Do not compare it to Scott's. Even the look-like prototypes don't even look as beautiful as his. So with that said, today I'd like to talk to you about some of the questions we ask. We try to think about how can we design transducers that are specifically for neurosurgical disorders. And we try to build them, again, in an academic setup. So the name of our lab is Happiest Lab, after the Greek god of healing. And in the interest of time, I'm going to skip quickly, but if you wanted to read more about it, you can go to hopkinsmedicine/neuro/happiest. For the lab, we have two founders, a PhD and an MD, much like that's the culture at Hopkins. It's very collaborative. And we're all about trying to really kind of like think about the marriage of two fields, sound and spine. So as you walk into the lab, you see illustrations that indicate that. That's a reminder for ourselves so that we can remember at the end of the day, we're trying to solve a problem. We're here for a patient. We're not here for our own H indexes. So as you enter the lab, we have a little Amazon or Siri that kind of helps us understand each day as we get spectral Doppler of like pig spinal cord or our own carotid or like wrists, we try to hear that. And when we're trying to build this lab, we notice that there's no even such databases. If you Google the sound of the spine, the sound of liver, there's no such database. So we try to listen, and by listening, I mean like ultrasound listening. And similarly, there are visuals as you walk into the lab so that, again, it's a reminder that there's no one person trying to solve this. One of the missions of our lab is to come together to solve spinal cord injury. So as you can see here, people from all around the world are coming together to focus on a really ambitious project on spinal cord injury using sound. And so in this audience, I don't have to tell you about all the different applications of sound. Obviously, sound has many capabilities. We can think about the imaging aspects. We can think about the remote neuromodulatory aspects. We can think about non-invasive or minimally invasive ablation aspects, or direct delivery or piezo surgery, whereby you can cut the bone and leave the surrounding neural or soft tissues or vasculature safe. So again, spinal cord injury is such an unmet need, and sound has so many different applications. On a daily basis, day in, day out, and an hourly basis, we try to think about how can we tackle and how can we help this problem. So when we're trying to do a literature search, this is Brian Huang. Dr. Huang is a PGY7 neurosurgery resident. So he had a researcher with us, and he helped me and Dr. Theodore trying to understand what exists out there. And essentially, as much as we really try to dig hard in terms of, sure, ultrasound can do imaging, flow sensing, high intensity focus ultrasound, low intensity focus ultrasound. At the end of the day, the conclusion was that it's an uncharted territory. It's a wide open field. And so as much as it sucks for our patient, it also means, how come nobody else has like really thought about this? And so there was a reason, because it's a lot to do. And so maybe we're just naive, but naive is sometimes good in the world of science. Speaking of being naive, I can tell you all about the 20, 30 plus rejections I got from the grants, and submitting to the NIH Trailblazer that Boise was telling me about. Thank you for helping me with your sample. Submitted once, NIH was like, well, this is, you have data, right? You can't. So I pulled that one figure out, and then they were like, well, you don't have data, this is just concept. And then for K99, when I was control F-ing, I think I was telling you about this, when I was trying to control F the word naive and ambitious, it came up 17 times. My score was 20, but still, like, they saw this very naive. And I think that's the type of stuff the Department of Defense loves to hear, when you're too naive for incremental, one step at a time thinking. Very understandably, different agencies have different missions. So DARPA came in and they decided to fund somebody who's naive. And so with that said, let me say a little bit something that may be out of the context of the ultrasound world. So spinal cord injury comes in two phases. If Chris Reeves is doing horseback riding, or whether it's a soldier in battlefield clinic, or whether it's NFL player, when spinal cord injury happens, unfortunately, there's not much you can do. There's a mechanical insult, direct insult to the area. And you probably know neurons can't regenerate. So there's not much we can do about the primary region. However, you've probably heard about time is brain, right? In the context of stroke, traumatic brain injury, similarly for spinal cord injury. Trauma at the end of the day is a neurotrauma at the end of the day is a trauma. So what we can do, what we're hoping to do is, how can we look into monitor and the secondary injury? Like we're talking about the penumbral zones, the neighboring surrounding tissue. So can we monitor in real time, postoperatively? And if we can we do something about it? So when I first joined, Hopkins May 2016, I think it was probably 5.5 years ago. Jeff was the first person to recruit me. Through him, I got the chance to talk to Nick Theodore. And the first thing he told me, he was like, can we using our, sound, keep talking about sound, can we like see blood flow? And I'm like, of course, Doppler ultrasound, right? Maybe I should have been a better listener. I talked about listening. What he was really talking about wasn't blood flow. He was talking about tissue perfusion. So we're talking about slow flow in small microvasculature. And for scale purposes, spinal cord injury is a pinky finger. So some of these things are like 50 microns, 100 microns. And then again, back to the problem. The hypothesis is, if there's a mechanical insight, if there's a primary injury, is there a way for us to monitor the blue penumbral secondary injury? Is there a way for us to do something about it in real time? Because again, time is brain, time is spinal cord. The difference between a few hours is somebody moving their hands or not. So I think hopefully I've addressed to you that there's currently no method to ensure tissue health post-operatively. So if something happens again in NFL, if somebody is thought to have spinal cord injury, they're taken to the operating room. These bony landmarks are taken out. The bony landmarks are called lamina, so the process called laminectomy. The hope is something that's called decompression. So if you have trauma, if our fingers gets broken, like it swells, right? Same thing with neurotrauma. So same thing with neurotrauma. When spinal cord injury happens, spinal cord swells. So if you just let those cerebrospinal fluid around that, if you let the bones like press on it, that's devastating. So the thought process can be kind of do something called decompression, means like, let's drain the CSF, cerebrospinal fluid, or they increase the mean arterial pressure so that there's more, in the hopes of more blood flow coming to the region. Now, watching this as an engineer, you keep asking, okay, how much do you increase? And hearing that there's no feedback loop mechanism, the term you want to hear as engineers, it's scary because if they increase the mean arterial pressure too much, the patient can go blind. And when you talk to the senior surgeons, they're like, yeah, I know what I'm doing. When you talk to the residents, they're like, heck no, there's no way to quantify this. So we need something that tells us. And so for us to quantify it, we thought about a gadget. And again, Nick Theodore's idea was, can we have a conformal flexible Band-Aid that as I'm doing this anyways, that I'm doing this laminectomy, can I just place this Band-Aid on top of this protective layer of spinal cord called dura and let it do stuff that you're telling me sound can do. So we envision a Band-Aid that's omnisonic, meaning it has all the different applications of sound. It can do imaging, real-time imaging, it can do flow sensing, and if there's something wrong, it can do therapeutic ultrasound, neuromodulatory effects, or lay audience like the physiotherapy for spinal cord. So thanks to DARPA, we were able to assemble a world-class team from around the nation. Specifically at Hopkins, we were multi-institutional, multi-schools. We were working with engineering, biomedical engineering, radiology. We have an ethicist at public health, and we work with APL, Sonic Concepts, who builds ultrasound transducer. Columbia, who helps us with the A6 chips that Scott, you were talking about, the ability to wirelessly charge these things and transfer data. They have regulatory consultant, and most importantly, a patient advocate. And we keep recruiting. So if you're interested, we'd love to hear from you. The team is getting to 60, 70, so I can't keep account of names anymore. But we do need the best of talents because this is such an ambitious and futuristic project. When we're thinking about what devices we need in the lab, thinking about Carnegie and like the way Jeff has set up Carnegie, I thought about what devices do we need so that it's actually translatable. So when we talk to our radiology colleagues, Javad, Jennifer, our radiologist, and Beth Smith, our chief sonographer, they're on our team for DARPA. When I asked them what system can be used so that actually we can translate them, they were like, well, use the exact same system because if you have a code, if you have a hardware, like it needs to work with that. So it sounded like we're talking about 2018 at this point, pre-pandemic. At that point, the state of the art for to do microvascular imaging was Philips Epic 7, which is microflow imaging, and Canon Aplio Superb Microvascular Imaging. So we got the two systems and we tried to see what can we do with that. So again, we're trying to push the boundaries of how slow the microvasculature and how slow the flow can we see. And these are some of the SMI modalities, super microvascular imaging in PIC spinal cord injury. Beautiful, really amazing. Can we build a sensor that does the same thing? To be known. We're working on it. It's a year out of a 5-year project. We need to be in human by the 5th year. So one of the projects that we tried to do is, instead of starting from spinal cord, we start from a fingernail bed because the microvasculature are resembling. And so we really compared the two systems I told you about, 6 different linear ultrasound probes, and the different modalities, color Doppler, power Doppler, and the microflow imaging I told you about. And we really tried to understand under what parameters, what frequency, what power, what dynamic range, and what type of images do we get. So we set up a study design, both in vivo as well as how in vitro, to see how small can we see and how slow can we see, how slow can we detect, and using what probe, what modules. So here you can see some of the results. In the interest of time, I'll skip that, but happy to chit chat about that. Key take-home message is that if you want to design something, you can't hit a target you can't see. So you need to really think about your design specs. The ultimate goal, whether through in vitro, animal surgeries, or human studies, is for us to be able to understand what we need to build. And here you see Eric Westbrook dropping the weight on takes spinal cord, induces surgery, and goes on. The ability for us to do translational work. Because as we build these gadgets, we go into pick surgeries that we want to fail. We want to fail, and we want to fail fast. We want to learn the same day that that's a bad idea as opposed to waiting another year. So as I mentioned to you last week, we had our lab opening. So if you guys want to look into some of the things we do there, feel free to watch the tour here. We're located in Bayview. It is a little bit distance from here, but we love it there. It's about 4,000 square feet that was given to us as you walk in. I hope here, maybe I can get rid of this. But something I had here was like some of the jargons, like, it's more common in engineering design, the type of stuff Nick Durr is teaching. I think he's on the line. So like, R&D, V&V, when you do research and development, verification and validation. So this is our research lab. And if you think about, if you look at this, this is our imaging lab or ultrasound lab, or we call it design lab, could be R and D. This is where we develop things. V and we verify things according to specs, against specs, and we validate them in our sim center. So as you enter into the room, the very first table you see is the sonography table. Again, we work with our radiologists and sonographers to understand what specs we need to design against. This is Dr. Fariba Al-Baglu. She's our postdoctoral scholar. The type of science she does in the lab is concerning these things. So Scott mentioned butterfly IQ and everything else. This is Haley Abramson. She's our computational person. She tries to, when we get those beautiful SMI images, she tries to go to a number, because Nick, as a neurosurgeon, he doesn't want to see like .com images with like heavy files. He doesn't want to open them on his phone. He just wants to see a number that tells him whether the tissue perfusion, whether the tissue health goes up, stays the same, or goes down as a function of time. The next table we'll see in the lab when you come in, hopefully, is a fundamental engineering / physics acoustic table. This is a water tank. You can see here there's a water conditioning unit, because when we first tried to do this, everything in the lab was working. We're going to the pics, nothing was working. So the difference was temperature. And so aside from that, water conditioning as well. So in addition to imaging, I mentioned in addition to our linear acoustics, we are also concerned with nonlinear acoustics. And so we look at the neuromodulatory effects using our new FUS probes under NeuroNav, because we don't want to burn the wrong places. So we have 0.5 megahertz, 1, 1.5, and 2.5 megahertz. On the left is an in vitro study by our electrical engineering master student. On the right, you see Beth Smith, our chief sonographers during the animal surgeries. Finally, I think I would like to mention, remember R&D and V&V analogy. I'd like to wrap up by saying we have a manufacturing capability there. We have our metal 3D printer in the lab, because Nick wants a lot of like rods and screws and implants that requires to hold the probe there. A typical laser cutter, vinyl cutter, 3D scanner, 3D printer. This is our Richard Mejia, our lab manager working at the furnace in our machine shop. And this is the type of stuff he's been able to print with metals, and a dicing machine that Scott is very familiar with when you want to build like or cut piezoelectric transducers. And these are 2 of our master students, Hopkins BME master students, doing their thesis in HEPIA Sim Center, because as inventors, we love our ideas, we think it's the best. Usually it's not until you give it to the end user and they tell you what's wrong with that. And with that, I'd like to conclude. I'd like to thank everybody who supported us to get here, and the people who are actually in the lab day in and day out on an hourly basis. They're the engines of innovation. And everybody who trusted us from DARPA, NIH, ICTR, NSF, MECO, and Harvard Design. And some of my relevant disclosures. With that, thank you very much for listening. I hope it was helpful.
Absolutely amazing. Amir, thank you very much. Got a great program starting up and you're just getting started. Congrats to you. Congrats to Dr. Theodore and their whole team. I know there's a lot of questions starting with biomaterials. I mean, you really got the wheels turning, in my view, about implantable ultrasound. It reminds me a little bit of what's going on in intracranial or cranioplasty with Chad Gordon. Absolutely tip of the iceberg of what we might accomplish. So great job. I'm going to steal your screen share and then quickly give it to Dr. Boctor. In the interest of time, we're going to skip the we're going to take questions at the end just to stay right on time in the interest of being able to go right up to 5 o'clock. I invite everyone to stay on afterwards. At 5 o'clock, we have a special presentation of a token of our appreciation for our keynote, as well as our invited speakers as well. Dr. Manbachi, thank you very much. Awesome. If you were a PhD student working on ultrasound, Dr. Manbachi was once in your shoes. And, you know, you have so much to look forward to. Thank you very much. All right. Okay, and plug in here. Yep, put your screen on the big display. We have about 20 people in the room here, and we had about 75 people online, really. So it's great to have, you know, hybrid is hard. Yeah, but it's great that we were able to bring about 100 people together today to hear this. Okay, now, are you in the Zoom meeting? Yeah, so just join the Zoom. Yeah. Open. Good. Share your screen. Join with audio. Share your screen. The whole screen over. That'll do too. Yeah. Share. Unmute. On video.
Disappeared with me. And then I'll try to work.
Yes, I think we're on. Excellent.
All right.
So our last invited speaker is Dr. Boctor. It's so great to see you in person. It's been a long time.
Yes, indeed.
Dr. Boctor is faculty with us here in computer science and radiology. He's worked on so many things. He's really been a hallmark of Hopkins ultrasound research for a long time. He's going to talk to us today about photoacoustic ultrasound. Thank you, Emad.
Thank you. Thank you, everyone. Thank you for the invitation. I'm really happy to give a talk in person. That's really different from all the online we've been doing so far, but I'll try to go quickly. So the talk is related to photoacoustic effective medicine, trying to explore new frontiers in this area. Here's my disclosure, conflict of interest managed by Johns Hopkins University. But before I really want to give a quick overview on the music lab, the medical ultrasound imaging and intervention collaboratory. So in the lab, we focus on co-robotic ultrasound, where a robot, we envision it's quite important because of precision and accuracy to be working in tandem with a radiologist, with sonographer. Many application and many needs we have for the robot, from converting the qualitative modality into quantitative, helping the sonographer to overcome this heavy duty work and kind of give him computer like hand-on-hand control, where the robot can place the effort and pressure. And on the other side here, we have advanced ultrasound imaging. This is the second thrust, where from the name, we are really concerned of finding new parameters for the ultrasound, measuring more parameters about our tissue of physiology, like temperature, oxygen saturation, voltage membrane variation, protein expression for aggressive cancer like PSMA expression. So we try to measure all these parameters. And here on the third thrust from the name, it's we focus on intervention, and this is where we use tools in ultrasound, biopsy, needle, catheter, and we realize that if we can make these tools smart, like speaking the same language, the ultrasound, we can do more things and more stuff. We can actually have cameras on the ultrasound probe, and that makes it like the ultrasound aware of the environment, and it's basically part of this thrust. The fourth thrust, which we call ultrasound bioeffects. As you all know, ultrasound is not just an energy to build this image. There are more than 20+ effects on our body. We can use ultrasound energy to open up ports in the cell membrane, sonoporation effects, sonochemistry. We can use ultrasound, as Amir mentioned, to activate, switch on and off cells, neuromodulation. So this is quite fascinating field where if we understand the mechanism of action and integrate it with imaging, sky is the limit really. So now, before I start, I really like to give the credit to everybody, real musicians who did the work, current members and former members, and really all the credit goes to the collaborator who give us the time and effort to work with us. Now, you know photoacoustic, and thank you, Baisi, for introducing it. So I'll go through it quickly. Everybody knows photoacoustic and why it's important. So my focus today is give you our effort and work in the neuroengineering part. And when we talk about neuroengineering, we really mean neuroimaging modalities. It's very important. We really need to understand the brain, so we need to measure everything about the brain. This figure gives you the landscape of all available modality, both in research and clinical market. Just to decipher it, please look into three important parameters: the temporal resolution, spatial resolution, and depth, and the invasiveness of the modality. And I'd like to add maybe one more parameter, which is mobility. It's not even mentioned here, but we really like to have an imaging modality that's mobile, wearable, give us enough resolution, enough depth, and spatial resolution. And it could be non-invasive, at least minimally invasive, to measure and unleash the function of our brain. If you quite see here, there is a quite gap. This is actually the needed area to cover, where we have millisecond resolution. We can actually have enough depth and enough resolution. This is kind of where we believe photoacoustic can easily come and fit this area. So let me take you into the challenge and describe one by one how we can make this happen. So to give you more example, what we mean by functional imaging, or in this case, the photoacoustic imaging. For the brain, it's an organ that we need blood supply to it. So it's very important to keep an eye how the brain is getting the blood and nutrient and oxygen. This is where we look at like the hemodynamics aspect of the brain and neurovascular coupling. But then the rest of the brain, the neurons, the circuits, it's definitely the way we study it, that we have to have a way to measure or evaluate the electrophysiology and neurochemistry. And if you look into the options we have today, the optical imaging does a great job in figuring out electrophysiology and hemodynamics, but it comes with a price. We really need to have a craniotomy. The depth is very limited, and that's what we can get from the optical imaging. MRI is great modality because in a non-invasive way, we can have a complete picture of the hemodynamics, the bold signal in the brain. But it cannot really do much about the electrophysiology and neurochemistry. PET comes and covers the neurochemistry area, but the speed and the resolution is quite limited. So what we hope to work on here is to see that photoacoustic could be the platform that allow us to do in a non-invasive way electrophysiology, hemodynamics measurement all at the same time. So let's start with the first challenge. We want to do photoacoustic imaging of deep neurophysiology and mainly to measure the hemodynamic response. For us to do that, this is basically work funded by an R1 with Dr. Ray Kohler and Ernie Graham. And what we try to do in this grant is to develop photoacoustic system using conventional array, and at the same time, have the ability to evaluate the sensitivity and specificity of this modality in a challenging hemodynamic scenarios. So for this reason, we developed this animal model, a piglet model, where we have, as you can see over here, the photoacoustic imaging probe, the ability to get real-time blood samples from the sagittal sinus at the ground truth. And then we have the ability to do control of the oxygen, graded hypoxia, unilateral ligation, bilateral ligation, and that's kind of more and more complex scenarios. And over here, what we do is we try to get the photoacoustic signal at different wavelengths and fit it into the right oxygen saturation curve. So we can get pixel by pixel measurement of what type of oxygen. That was the very first attempt we've done. Recent work published was basically using spectral decomposition approach. But then what I would like to show you here quickly is an ensemble of 15 different animals where we have, for example, graded hypoxia for 5 animals, unilateral carotid artery occlusion, bilateral carotid artery occlusion. And the data you see here is quite good agreement between the ground truth measured directly from the SSS location and the photoacoustic measurement. And we wanted to extend this one more. What if the hemodynamic challenge we have here is creation of a stroke? And we basically did same work in terms of 3D photoacoustic scanning of in a non-invasive way. And through the oxygen saturation map, we managed to identify a lesion that's really detecting basically the stroke-induced infraction model we have here. Now, going to the second challenge, how we can use ultrasound to measure electrophysiology. You know, it's in the beginning, it doesn't make an easy really answer. We have electricity, we have mechanical wave. So we had to start, this was a work funded by a BRAIN initiative. We had to start from a place where we, lucky enough to work with Dr. Laszlo, one of the pioneers who developed voltage sensitive dye in Yukon. And the idea is people in optical imaging field, they rely on voltage sensitive dye. And from the name, these dyes change the fluorescence signature based on the depolarization state. So one family of these dye called self-quenching dye, in the resting membrane potential, the dye goes inside and quench, and fluorescence really suppressed. During action potential, it goes out, and the fluorescence is amplified in this case. So the idea was, yeah, I stay here. Sure, maybe I can use my cursor here. Very good, sorry. So the idea was, let's just give it a try. We'll use one of these dye from Dr. Laszlo, and we want to see if there is a change in the optical absorption coefficient, because that's where photoacoustic will be directly related to. So we learned from his lab the cell membrane, artificial cell membrane model, lipid vesicles model, where we can freeze in time the electrophysiology state. So if we inject the valinomycin, then we can get the dye inside and stay there as long as we want. We get all the measurement we want. If we want to mimic the depolarized state, we just inject gramacillin, and then the dye will go out. And then we have all the measurement. On the right here, that's what the dye is good for. It provides us 40% fluorescence field. And we were really lucky to find that absorption really changed by 3% from depolarized to repolarized state. And we thought, that's really great. We should expect 3%. When we did the photoacoustic measurement, we end up with a difference close to 13 to 15%, which is too good to be true. Initially, we thought something wrong. We have to repeat this experiment. I think we've done it for over 6 months, and at the end, the conclusion is the same. And then at the end, we realized that, you know, that's physics. There is a conservation of energy phenomena here. When the fluorescence is quenched, there is more energy for photoacoustic thermal expansion and the other way around. So this reciprocity relationship basically made it easy for us. The reason why we have 13%, part of it from the absorption, part of it from the fluorescence here that was quenched. With this encouraging result, we went right away to an in vivo model, and we thought, let's just see if we can image a seizure in real time. What you see here is the same model. We have the rat, the photoacoustic setup. This is basically a typical photoacoustic. And what you see here is the absorption spectrum for the voltage sensitive dye. There is a nice peak right at 790. And this was very important for us because 790 is an isoplastic point where hemoglobin and dexhemoglobin crosses. And we thought like maybe single wavelengths will be sufficient at this point. And when you see here 3 different protocols for control. So one protocol, the one on the top, we don't inject voltage sensitive dye and initiate seizure and try to image. The second protocol, we inject voltage sensitive dye, but we don't initiate seizure. And of course, the third one is when we have seizure and voltage sensitive dye. And the algorithm was quite tailored to the scenarios we have here. We have voltage sensitive dye that is considered low speed, response time within 1 second. We have low speed laser system. At that time, we didn't have access to the kilohertz laser system. So we built a short time Fourier transform looking for this few frequency component. And I'll show you the result here for the 3 different scenarios. Seizure control, we have seizure, but VSD injected. No VSD, but seizure is on. And here is where the seizure activity is going on. Now, we further validated the work with the neurochemistry. So we put a catheter similar to the one we have in the SSS to keep drawing the glutamate release and correlate that with the blood. The further testing we did was with the visual cortex. We wanted real control. So the idea here, instead of having seizure where the activity is going all over the brain, what if we have a controlled visual stimulus on one eye or both eyes, And then we will be able to record the visual cortex. And you can hear here the VFD control. We did not inject VFD, and there is stimulus. And this is with the VFD control. And just for the interest of time, I'll go over this part and then describe the application. Now that we are able, with photoacoustics, measuring both electrophysiology and hemodynamic response, the focus clinical translation was in pediatric medicine. So we thought one of the areas that needs help is a hypoxic ischemic encephalopathy. A newborn, if they have HIE, it really can go without even notice. There is no any standard. In fact, the standard that we have today is the EFM, or the electrofetal heart monitoring. It's a flawed standard. The way it works, you keep monitoring the heart rate of the baby, the contraction cycle, and from there you will be able to evaluate whether there is an HIE or not. A recent publication by JAMA, they basically found out that this is not a standard, something that we inherited from the medicine in 70 and 80, and there is no really solid evidence that it actually prevent or early detect HIE. So they said it quite clearly, it's a flawed tool. And this figure said it all. From 1980 and even before that, the HIE or cerebral palsy didn't change about 3 every 1,000, despite the spike in severity. So it's a serious problem and need a monitor. Our approach, instead of monitoring heart rate to evaluate the brain health, we should really go and check the brain. So we want to replace the laser with LED, safer light source. And in this work, we explored deep learning to minimize the number of firing, enhance the signal from the LED excited photoacoustic effect. We even went further and said, like, so far what we're doing is passive differential, but we would like you to do active differential diagnosis, because we cannot inject voltage-sensitive dye in the baby, but we want to measure something related to the stimulus. So what we've done here is we thought, let's use ultrasound as a source of a stimulation, neuromodulation source. The idea is very simple. If we can measure hemodynamic response, followed by controlled ultrasound neuromodulation, followed by yet again another or continuous hemodynamic response, we can have a clear signature of the health of the brain, both in the hemodynamic and also on the neuronal function. We did the early testing on cell culture, basically brain hippocampus neuronal cells. The purpose of this study is to optimize the neuromodulation protocol, what type of frequency, what type of signal we need to fire. And then we have a cell culture protocol mimicking the stress that we encountered during labor. You have an episode of oxygen glucose deprivation during contraction, followed by normoxia, followed by ischemia, normoxia. So we did this protocol and we found out that when the cell is under stress, they fire more often. So we took this and recently we validated in vivo. We have an ultrasound neuromodulation system similar to the one Amir showed it to us. And what you see here, we replicated the hypoxia protocol. So we start with 15-minute baseline and then hypoxia, asphyxia, and recovering afterward. And you can see the activity is really spiking. That's an EEG recording right after the hypoxic episode. Now with the recent funding from JHTV, we're now planning to translate this technology into a device that hopefully will be used on human one time. The device should look like a small endoscopic device, like a catheter kind of form factor. We don't need it to be imaging. It could be just simply single element, and that will allow us to measure the hypoxic response, allowing neuromodulation. And we realized that we can actually go further, not just measuring the brain function of the baby, but also the placenta, the source of blood. So we have differential diagnosis in both places. And this recent result, probably you're the first audience to see it. This is from a rabbit pregnant model where we have fetal brain and the placenta imaged together. And our ion translation is we're working with a small animal company to translate some of the animal research work we've done. And recently we have a good partnership with Brimrose to take the technology to the clinical market. The conclusion is ultrasound is awesome. I mean, there is so more and so awesome things need to be done. And the field is yet to really give us more and more opportunity. And with that, I think I'd like to say thank you for your time and for the invitation.
Dr. Smith, would you like that question for Dr. Boctor?
Okay, I should stop share. Yep. Leave.
The neuromodulation aspect of things, or neuroexcitation. Do we have a good understanding of what the mechanism is behind that? Is that going to be something that's
Nobody knows. It's a big question. There are different hypotheses, but I am leaning toward the hypothesis. It's not a mechanical effect. There is basically a mechanosensitive ion channel that act like a piezoelectric sensor. So, and that there is more evidence to let us believe that this is probably the mechanism. How it works is a single mechanosensitive channel. Is it a combination? We don't know. There's active research going on, and I really expect within a year or two we will see a big paper about the mechanism of action itself, probably unleashed somewhere.
Excellent. Thank you very much. Thank you, Dr. Boctor. Thank you for that question as well. So as we conclude, thank you for staying with us. Stay with us for just a couple of minutes longer, because I want to thank you to the invited speakers and extend a small token of appreciation to everybody on behalf of Hopkins BME. I just need my cameraman. And so do your best to keep us in frame, and I hope you're seeing.
Targeting over there.
Excellent. Very good. That's what we want. We want to be targeted. Excellent. All right. So if you followed the BMEX seminar series, then you know that the X stands for translation. And you know that we give an XC. This is the XC. It is the much coveted BMEX token of appreciation for our invited speakers. And I want to start with a small token of thanks for Dr. Bell. Liza, you got us started today in just the best fashion. Thank you very much. Liza, thank you so much. All right, and next up was Dr. Ding. Kai, come on up. And Kai, you two are now an XC award winner. Thank you very much. I was fascinated, and I'm so glad, Dr. Smith, that you also talked about ultrasound and radiotherapy. It's really interesting to hear that that's on your mind as well at GE. And I'm just fascinated that piezoelectric crystals will hold up at high doses. It seems like that should disrupt the crystal lattice. Maybe we can talk about that at dinner.
Thank you.
All right, thank you very much. And next up is Dr. Manbachi. Thank you very much. Amir, let's give Amir a hand. Amir, this is your XC. There are many like it, but this one is yours. Thanks very much. Can I borrow your XC? Because I'm so glad you joined us in person today. I thought you were joining by Zoom, so I only brought 3. But they always on my desk, so that's a good. All right. Okay, and then last up is Dr. Boctor. Thank you. Come on up, Dr. Boctor. Give Emad a hand. And or next thing that you can type Amir for. No, there really is a force. So thank you, one and all, our invited speakers. Now, for the keynote, you see our 3D printer has been working overtime. Yes, so this one definitely has your name on it, and shows some representation of what you've had so much to do with over the last 40 years in ultrasound and making such a great impact. Scott, it really was an awesome pleasure and an honor to have you with us.
Well,
and so that is yours.
Really neat. And yeah, this is going to be a big hit.
If you put an LED in it, it's photoacoustic.
Did anybody go to the ultrasonic symposium in 2004 in Montreal? They had this really cute little 3-colored LED thing that I think I may be able to mount underneath it. I have had an absolutely wonderful day here, interacting with students, professors, fellow speakers. Jeff, thanks so much for arranging it. This has just been phenomenal.
It's absolutely our pleasure. Thank you very much for sharing your day with us. And thanks everybody for staying and sticking around. Great to see you in person, and hope to see you again soon. All right, thanks.